to lesson 1, properties of sound waves. Sound, what is the sound? Sound, it's an external factor that affect our ears, causing hearing. And we sound produced from the vibration of objects, from the vibration of any object. When the object is in a vibration state, it will make a sound, but when the vibration stops, the sound will stop. What is the nature of sound wave? In the last lesson, we studied that the sound is mechanical longitudinal waves. Mechanical because it can't propagate through vacuum or it needs a medium, and longitudinal because it composed or consists of compressions and rarefactions. Sound wave propagates through media as spheres, like the spheres. The sound waves has the sphere's shape, and the center of the spheres is the center of sound source. Like here, he is holding a source of sound, and the sound is propagating as spheres, and the center of the spheres is the center of the source of sound. That's why we can hear the sounds from all the directions. Give reason, we hear sound from all directions that surround the sound source because sounds propagate as spheres. What is meant by the wavelength of a sound wave is 1.5 meters. The wavelength, as we studied before, is the center between two successive compression or two successive rarefaction equal 1.5 meters. Sound velocity or the sound speed, it is the distance covered by the sound wave in 1 second. And as we know that the sound wave propagates through different media with different velocities. And as we know before that the sound velocity through solids is the largest one, the largest velocity, then the in, then the less velocity in liquids, and the smallest velocity in gases like air. And the sound velocity through gases or air equal 340 meter per second. To calculate the sound velocity, we can use this rule: sound velocity equal wavelength times frequency, and the measuring unit of sound velocity is meter per second. Here in this problem, we need to calculate the wavelength. If we want to calculate the wavelength, so we will make the sound velocity over frequency. Sound velocity over frequency. Okay, so but here the frequency equal 10 kilohertz, but we need to use the frequency in hertz, so we will convert from kilohertz to hertz. So we'll take this number 10 times 10 power 3 to convert it from kilohertz to hertz. Problem 2, it is the same idea. We need to calculate the wavelength, so wavelength will equal wave velocity divided the frequency, and the frequency here it's in hertz, so we don't need to convert it. Here we have the properties of sound waves. We'll talk about the properties of audible sounds. Audible sounds means the sound that we hear. We have two types of audible sounds: musical tones and noise. Musical tones, they have uniform frequency, and that's why they are comfortable to be heard, like violin, piano, and reed pipe. But the noise, it's non-uniform frequency. The frequency is not uniform, that's why it's uncomfortable to be heard, like the loudspeakers and the drill and the car horns. We can differentiate between the different types of sounds, or between the different sounds, by three properties. Like we can differentiate between the man voice and the woman voice, between the lion voice and the bird voice, between the shouting and whispering. We can differentiate between all the types of sounds um, in three properties, or through three properties, which are: number one, sound pitch; number two, sound intensity; number three, sound quality. We'll start with the sound pitch. Sound pitch, it is a property by which the ear can distinguish between rough or harsh and sharp voices. And we have two types of sound pitch: low-pitched sound and high-pitched sound. Low-pitched sounds, they are the rough or harsh sounds, and they have low frequency. So low-pitched sound and low frequency, like the man voice and loud. But the high-pitched sound, like the sharp or soft sounds, they have high frequency, and it's like the women voice and bird. So high-pitched sound, high frequency. Like here, in these waves here, we have a high frequency, so it's a sharp sound. But this one, it's low frequency. The frequency here is less than there here, so it has a low-pitched sound or rough sound. The sharpness of sound increases as the frequency of the source increases. The more frequency we have, the more sharpness sound we have. Activity number 2, if we have two test tubes, if we have two tested tube and we put in one of them, we put in both of them water, number one will have a large amount of water, but number two will have small amount of water, like that. Okay, so number one have a high amount of water, but number two have a small amount of water. So the air here in number two is larger than the amount of air in number one. If we make any voice at the top of the both of them, if we make any voice at the top of test tube 1 and at top of the test tube number 2, and then we will compare between both sounds at 1 and 2, we'll find that here at 1 the sound will be sharp, but the sound here at 2 it will be rough. Why? Because the sound wave here it can't find a space, so it will make very large waves, it will make more waves, so the frequency is high. But here in 2 the frequency it can find more space or more air, so the frequency will be less frequency, because here it has high frequency, so it will be a sharp voice, but here it have less frequency, so it will be a rough voice. So by increasing the length of air column, the sound will be rough because the frequency will be low. Activity number 3, to determine the frequency of a known tone. If we have a known tone and we want to know the frequency of this tone, we'll use a device or an instrument called Savart's wheel. Savart's wheel here, we use it to we use Savart's wheel to determine the frequency of a known tone. The steps: first we listen to the tone for a while, the tone that we want to calculate its frequency. Then we will rotate the Savart's wheel with different speeds, and until we hear the same tone we want to calculate the velocity, its frequency. Then we will calculate three things: number one, the number of cycles; number two, the number of teeth; then the time we need to get to the tone we want to calculate its frequency. Then we use this rule: frequency equal number of cycles times the number of teeth over time. Number of cycles, its symbol is D; number of teeth, its symbol is N; and the time T. So D times N over T. Here we have a solved example. What is the frequency of a tone produced by Savart's wheel that rotates with velocity 900 cycles in 3 minutes? The number of teeth of this gear is 30 teeth. First we should convert the time from minutes to seconds. So we have 3 minutes times 60, so we have 180 seconds. Frequency equal, as we said, D times N over T. D is the number of cycles, 900, times the number of teeth, 30, over time 180, so the frequency will be 150 hertz. The sound pitch increases. The sound pitch increases by increasing the frequency. High frequency, high pitched sound, and sharp voice. So the sharp or soft tones have high frequency, while the harsh or rough tones have low frequency. Number 2, we have the sound intensity. Property number 2, sound intensity. Sound intensity is a property by which we can differentiate between weak or strong sounds. Like shouting, it's not like whispering. Shouting is a stronger sound, but whispering is a weak sound. Okay, so the intensity of the sounds related to the energy. The more sound energy, the more sound intensity. If the sound energy is high, so it gives a strong sound, but if it's low, it gives a weak sound. And the level of sound intensity changes from one person to another. Sound intensity are not the same for all persons. It differs from one person to another. The measuring unit of sound intensity is watt per meter square, but the noise intensity is measured by decibel. We have 5 factors affecting the sound intensity, which are: number 1, distance; 2, amplitude; surface area; density; 5, wind direction. We'll start with number 1, distance between the ear and the sound source. By increasing the distance from our ears and the sound source, the sound intensity decreases. So increasing distance, sound intensity decreases, so it's inverse relation or indirect relation. So we have here indirect relation between sound intensity and the square distance, d square, and that's a law called inverse square law of sound. Inverse square law of sound, it is the intensity of sound at a point varies inversely with square distance between this point and sound source. And here we have I for intensity in direct relation with square distance. Factor number 2, amplitude of vibration of the sound source. If we have a ruler and we put it on a table and we will push the ruler to move up and down to make amplitude, it will make also a sound. But by passing the time, the amplitude will be decreasing and the sound intensity will be decreasing. And if the amplitude increasing, if the ruler moves up and down for large distance, the more we have, more sound intensity or stronger sound intensity. So the sound intensity directly proportional to the square amplitude, so it's a direct relation. Notes: sound intensity decreases gradually by decreasing amplitude, and the sound intensity is directly proportional with the square amplitude. When the amplitude increases 2 times, the sound intensity will increase 4 times, because it's a direct relation between amplitude, between intensity and the square amplitude, so it will increase 4 times. Factor number 3 is the area of the vibrating surface. If we have a phone call and we will make a vibration in our hands, and we'll put another call, another phone, and we'll make the vibration sound, but in a resonance box, the resonance box here, and it's a wooden box which is empty and open, has an opening from one side. Both phones are on vibration, but the sound intensity from the phone which is put on the table is stronger than the vibration or the sound of vibration which is in our hands. So the phone on the table has a stronger sound. Why? Because the resonance box has more surface area. So by increasing the surface area, the sound intensity will be increase. So it's a direct relation. That's why the strongest musical instruments like guitar and violin are fixed above a wooden box. Why? To increase the sound intensity. Number 4, medium density. We have a device here, and this device can vacuum the air. We will put an alarm inside this device, and before vacuuming the air, there is air here in this device, and we'll make the alarm make a sound, and we will listen to the sound. Then we will repeat the same steps, but after vacuuming the air, after taking the air out from the device. So there is vacuum here, and we will make the alarm making a voice or a sound. We can't, or the sound after taking the air out is less than or weak, and the sound of the alarm with the air on is stronger. So in the case of air, the sound is stronger than the case of vacuum, or there is no air. Here, observation: the sound is weaker after bombing the air out. Sound is weaker after bombing the air out. Conclusion: sound intensity is affected by the density of the medium that transmits the sound. The more density we have, the more sound intensity we have. Sound intensity increases as the density of the medium increases. That's why the sound intensity in case of carbon dioxide gas as a medium is higher than that in case of air. Why? Because the density of carbon dioxide gas is more than that of air. Density of carbon dioxide more than the density of air. Factor number 5 is the wind direction. If the sound and the wind direction are in the same direction, so the sound intensity will increase. But if they are in the opposite direction, the sound intensity will decrease. So same direction, sound and the air in the same direction increases. Opposite direction decreases. Here we have a live application, which is the air plugs. Air plugs are made of silicon, and it takes the shape of the external ear canal, and it is used to avoid the noise, hazards of noise, or the danger of noise. The property number 3 is sound type or sound quality. Sound quality is the type, it is the property by which the human ear can distinguish between different sounds, even if they are equal in intensity and pitch. If we have two sounds and they are equal in intensity and pitch, but we can still differentiate between them through sound type or quality. Example, the tuning fork, it has a simple or pure tone known as fundamental tone, but the violin or piano, it has a complicated tone. Okay, notes. Um, we have the fundamental tone, and the fundamental tone is associated by several harmonic tones, and both of them, fundamental and harmonic tones, will produce the complicated tone. So the complicated tone consists of fundamental tone and harmonic tones. And the harmonic tones is higher in pitch and lower in intensity than the fundamental one. So harmonic is higher in pitch and lower in intensity. The harmonic tones differs from one source to another depending on the nature of sounds. Each sound source has its harmonic tone, its own harmonic tone. So harmonic tones, they are tones that accompany the fundamental or basic tones, but they are lower in intensity and higher in pitch. And it differs from one instrument to another. That's why human ear can distinguish between sounds from different sources. We can differentiate between the sound of piano, the sound of guitar. Why? Due to the harmonic tones that accompany the fundamental tones. Types of sound waves. We have three types of sound waves. Number one, audible sound or sonic waves, and their frequencies ranging between 20 to 20 kilohertz. And the human can hear this these voices or these sounds. So here we have a give reason. Human ear can hear sounds of frequencies ranging from 2 to 20,000 hertz or 20 kilohertz, because the ear transmits the effect of this sound to the brain. Then the brain makes the ear hear them or less hear them or can hear them. Okay. Then we have the non-audible sounds. The non-audible sounds are two types. Number one, infrasonic waves and ultrasonic waves. Infrasonic, they are sound waves of frequency less than 20 hertz. Infra less than 20. Like the waves accompany plowing storms, or the human ear, and the human ear can't hear the infrasonic waves because they are less than 20 hertz, and we can hear from 20 to 20,000. Ultrasonics, they are more than their frequencies are more than 20,000 hertz or 20 kilohertz, like bats, the sound of bat or dolphins. Bats, dogs, and dolphins can listen or can hear to the ultrasonic waves, but we can't. Human can't. Dogs can hear all the sounds produced by man, because man produce sounds of frequency less than 20 kilohertz, and dogs can hear up to 50 kilohertz. And man can't hear sounds produced by dolphins, because dolphins produce sounds up to 120 kilohertz, but we can hear, or the man can hear, up to 20 kilohertz only. So we have three types of sounds: sonic, from 20 hertz to 20,000 hertz, and then we have infrasonic less than 20 hertz, and then we have ultrasonic more than 20,000 hertz. Infra less than 20 hertz, ultrasonic more than 20,000 hertz. Here we have some real life applications of ultrasonic waves, like in the medical field, breaking down kidneys and uterine stones without any surgical operations, diagnosis of male prostate gland or gland tumors. Number three, discovering malignant tumors or the tumors. In industrial field, like sterilization of food, water, and milk, because they can kill bacteria and stop the action of viruses. Military field to discover the landmines.